Hello, folks. This here is a dollar bill. And maybe you've gotten money from somebody for doing something before. And that person may have told you to make sure that you conserve your money. What that really means is don't spend your money all in one place. If you have money, you want to keep your money and not spend all of it recklessly. People for years have talked about conserving money and not spending it all, trying to keep the same amount of money they currently have. Today, we're going to talk about conserving something else. What are we conserving, though, in physics? We're conserving what we learned about last time, momentum. And so today's lesson is going to be all about the conservation of momentum. So what is conservation? We talked about conservation of money, meaning that you want to keep the same amount of money that you currently have. Maybe you've also heard of conservation in terms of the environment. We want to keep our beautiful planet the way it is and keep the forests and the rivers as clean as we possibly can so that they can stay the same for many generations to come. Conservation is a fancy way of really saying keeping the same. And that's what we're going to do with momentum. We are going to keep momentum the same today. And we're going to take a look at some examples where that's really important. Welcome to our first example of keeping momentum the same. Here I have two carts that are situated on a track. You might notice that these carts have different masses. They are the same cart basically, except one of the carts has this giant black box on top of it. And so that means that it has more mass. Now, in a moment, I'm going to send these two cars at each other, each with a certain speed. And they're going to collide, and they're going to have a collision. And we're going to say that the momentum is going to be conserved in the collision. Meaning however much momentum the cars had before they collided will be equal to the total amount of momentum that the cars have after they collide. So let's watch the collision, and then we'll talk a little bit about what happened. Here we go. 3, 2, 1. So what happened during that collision? Well, we had two carts. We had one cart on the left side, which had the black box on top of it. It had a pretty big mass. And then we had a cart on the right side, which did not have the black box on top of it. The mass of the cart that had the block on top of it was 0.75 kilograms. And the cart that did not have the black box on top of it only had a mass of 0.5 kilograms. Now, I sent these two cars into each other. Except if you watched closely, you may have seen that I sent the cart with the black box on top of it at a little bit of a faster speed than the other cart. Well, the cart with the black box on top of it, I sent off at a speed of 4 meters per second. Let's call that V. The other cart, I sent off at a slower speed, only 3 meters per second. So we had two carts heading in opposite directions that collided with each other. The first cart had a big mass, 0.75 kilograms, and was moving at 4 meters per second. The second cart, a smaller mass, 0.5 kilograms, moving at only 3 meters per second. So what can we do with this information? Everything that you see here is information about what happens before the carts collide. Well, we have mass and velocity. So what can we figure out about each of the carts? If you said momentum, you'd be right. Let's find the momentum of the cart on the left. Remember, momentum is simply mass times velocity. So I'm going to take my calculator and I'm going to do 0.75 multiplied by the velocity of 4 meters per second. And I find that the card on the left has a momentum. Remember, the momentum is given the symbol P of 3 kilograms times meters per second. Now, how about the card on the other side? Once again, I'm going to take its mass and I'm going to multiply it by its velocity. And so if I do on my calculator 0.5 times 3, I find the momentum of the smaller card is 1.5 kilograms times meters per second. But there's one last thing I have to do. Do you notice how I keep talking about this as v or velocity? Do you remember the difference between speed and velocity? Velocity includes direction, but speed does not. Since these two carts are traveling in opposite directions, we have to take that into account. So if we said that one car was going at 4 meters per second, we have to say that the cart going the other way is technically going at negative 3 meters per second. If it's moving the opposite direction, it would have a negative speed, or velocity, I should say. That would make the velocity of the second cart negative 1.5 kilograms times meters per second. So my next question to you is, how much total momentum is there before the carts collide? You might be tempted to say that there are 4.5 kilograms times meters per second total of momentum, thinking that you would just add these two numbers. You do add them, but keep in mind that one of them is negative. That means that to find the total amount of momentum before they collide, we have to take 3 plus negative 1.5. If I do that on my calculator, I will find that the total amount of momentum, so P total, is equal to 1.5 kilograms times meters per second. And I'll write that number off to the side and circle it a whole bunch of times. We'll talk about why in just a second. So now let's take a look at what happened after the carts collided. I'll draw a dotted line here. After they collided, you may have noticed that the carts stuck together. They were combined. So now we had one big cart with the black box still on it, but it was really the two carts that were stuck together that were now moving together. They were also moving to the right. Why would they move to the right? Well, it's simple. This cart that had the black box had more mass and more speed than the other cart. Therefore, it had more momentum. So let's calculate what happened after they collided. Do we know the mass of the combined carts? We do. Remember, the cart on the left was 0.75 kilograms. The cart on the right was 0.5 kilograms. To find the mass of the combined cart, all I have to do is add them up. So let me do 0.75 plus 0.5 on my calculator, and I'll find that they together have a mass of 1.25 kilograms. So now we know their combined mass. But how fast are they moving after they hit each other? We know they're going to move to the right, but how fast? Well, we're going to figure it out using math. Here's how. Remember what we talked about at the start? Conservation of momentum. That means that anytime that we have a car crash or a collision, momentum is conserved, meaning we keep, just like we kept our money, we keep the same amount of momentum that we had in the beginning in the end. And so we said the total amount of momentum in the beginning was 1.5 kilograms times meters per second. Remember, that came from adding up the individual momentum. Well, that's the same as the total momentum after they collided. So we know that in the end, the carts have a mass of 1.25 kilograms, and they also have a momentum of 1.5 kilograms times meters per second. Let's now find out the speed of the cart at the bottom using that information. All right, now it's time to do some calculations. After they collide, we know the carts combined to have a mass of 1.25 kilograms, and they still have the same total momentum as they did before they collided. The momentum was 1.5 kilograms times meters per second. So if we want to find velocity, we should go to our momentum equation. P equals m times v. But we don't want P. We want V. We want to solve for velocity. So we're going to have to divide both sides by the mass. That way we can get velocity by itself. So P divided by m equals V. That's the equation we should use to find the velocity after they collide. Let's do that now. Momentum, or P, is 1.5 kilograms times meters per second. And the mass is 1.25 kilograms. I'm going to do that on my calculator. 1.5 divided by 1.25. And that means that our speed is 1.2. What are the units? Well, the kilograms cancel, so it's 1.2 meters per second. And that seems right. Meters per second is a great unit to measure speed or velocity in. So let's recap, because a lot just happened there. We started out with a situation about two carts moving towards each other. We knew that one cart would win the collision because it had more mass and it had more velocity. So the carts collided and they stuck together. And we wanted to know how fast they would be moving after they stuck together. To do that, I found the total momentum of each cart, making the momentum of the second cart negative because it was traveling in the opposite direction as the first cart. I then added up the two momentum, and I got that the total momentum before the carts collided was 1.5 kilograms times meters per second. I circled this number a whole bunch of times because it was really important. Why? Because momentum was conserved. Just like our money and the environment, we wanted to always keep the same amount of momentum. So when we went to look at what happened afterwards, we knew that their mass had to be the two masses together. And we knew that the momentum had to be the same value as the total momentum before they collided. So all I had to do was just rearrange my momentum equation, and I could solve for the speed of the carts after they collided with each other. Let's take a look now at one other example that shows the conservation of momentum. Here are the two carts again. Now this time I'm going to have them collide once again with each other, except it's going to be a little bit different. Now this cart has two black boxes on it, so it has a bigger mass than it did before. Also, I'm going to only have one of the carts moving before they collide. I'm going to send this cart in with a really high speed. It will hit my more massive cart, and then they're going to move off together. Let's have a look. 3, 2, 1. So let's go back to the board now and take a look. What speed did those carts have after they combined? Well, we're going to use the conservation of momentum once again. So let's draw out what happened before they collided. We had two carts. One cart had two black boxes on it. So it had a pretty big mass. Its mass was 1 whole kilogram. We also had a second cart. This cart only had a mass of 0.5 kilograms because it didn't have the black boxes on top. But this cart was moving. And in fact, it was moving pretty fast when I pushed it this time. It was moving, in fact, at 5 meters per second. So that's my velocity for this cart. But what was the velocity of this cart? If you said 0, you'd be right. The velocity of this cart, since it wasn't moving, is 0 meters per second. So my question to you, how much total momentum was there before these carts collided? Well, to figure that out, what we have to do is our momentum formula, mass times velocity. So I'm going to take the mass of the first cart, 1 kilogram, and multiply it by the velocity, 0. Well, I don't even need my calculator for that. 1 times 0 is just 0 kilograms times meters per second. And that would be the momentum of the first car. How about the second car? Well, let's take the mass, again, times the velocity. 0.5 times 5. And I get a momentum of 2.5 kilograms times meters per second. Do I have to make that negative? No, I don't. And the reason being is that the carts weren't traveling in opposite directions. I only have to make one of them negative if the carts are traveling against each other. Otherwise, I don't have to worry about it. So how much total momentum do I have? Well, I would do that by adding 0 and 2.5. And if I do that correctly, my total momentum is simply 2.5 kilograms times meters per second. That makes sense. All of the momentum came from the second car because the first car wasn't moving. So let me circle this number a whole bunch of times because this is going to be the important number for my problem because this amount of momentum must be conserved. Action 1. So let's now take a look at what happens after the carts collide. After they collide, they are still moving. They are now combined. And we know that they're going to be moving in the direction the first cart was moving because it had more momentum in the beginning. Well, what do we do here? The momentum of this cart plus this cart was 2.5 kilograms times meters per second. But what is the combined mass of the carts? Well, just add them up because they're stuck together. 1 kilogram and half a kilogram gives me a mass of 1.5 kilograms times meters per second. So to figure out what the total speed of the second cart is, I have to use the mass of the combined carts. And this should be kilograms. I'm sorry, I mixed up my units. And the combined momentum is going to be 2.5 kilograms times meters per second because it was conserved from the before. So if I want to find the velocity, I just have to use the momentum formula again. Let's do that now. P, or momentum, equals m times v. I'll divide both sides by m to get v by itself. And that means that P divided by m equals v. So plugging in some numbers, the momentum is 2.5 kilograms times meters per second. The mass is 1.5. kilograms times meters per second. And all I have to do is just divide these numbers. And again, this should only be kilograms. I keep writing the wrong unit for mass. And cancel out the kilograms. Let's do that in my calculator. 2.5 divided by 1.5 is 1.67, or 1.66 repeating, meters per second. That is the combined speed of the carts after they have their collision. That may have seemed very math heavy what we just did, but the concepts are really important to understand. Momentum, just like money and just like the environment, is always conserved. That means we always keep the same amount of momentum before a collision happens and after the collision happens. So, to solve problems like we just did, figure out the total momentum before two objects collide, and that's the same total momentum as there is after the objects collide. Then, once you combine up the masses, you can easily divide out and figure out what the speed is. Remember, the total amount of momentum before the collision is always the same as the total amount of momentum after the collision. That's the law of conservation of momentum. Thanks for watching.